Here in example 5 of our Module 4 class notes, once again I'll say, if you haven't yet watched example 0, my introductory video, please do so, where I introduce the characteristics and vocabulary of rational functions. Moving on from there into a discussion of example 5 here, we find a relatively simple in terms of factoring and the number of terms involved, a relatively simple rational function, but one that has a subtlety to it that's important that we take a look at. So let's see, let's approach this problem, let's start this problem the same way that we've looked at all the other examples in this section, in this module, by first of all factoring. We factor that denominator to x times x minus 1, and then we see something interesting happen. The x factor in the numerator can cancel with the x factor in the denominator, and I reduce that fraction down to 1 over x minus 1. That's something that hasn't happened before, a factor in the numerator canceling with a factor in the denominator. Let's see how that affects the behavior of the graph and the calculations that we do in working through this problem. First of all, it's important to note that even though we've reduced that fraction down to 1 over x minus 1, it's still true that the original function had an x factor in the denominator, so it's still the case that x cannot equal 0. Even though that's not the case in our reduced fraction here, the original function still had an x factor in the denominator, so we still have to note that x can't be 0, and that's going to factor in then, sorry for the pun there, that's going to factor in to our domain discussion as we look at the unreduced denominator of x times x minus 1 and say neither of those factors can equal 0. In other words, x can't be 0 and x can't be 1. So our domain is everything except 0 and except 1. Now for intercepts. You caught me in example 4 where I tried to plug in x equals 0, but it didn't work. Let me stop myself here and say, wait a second, we just said in the last slide that x can't be 0. So for my intercepts, I can't have a y-intercept because x can't be 0. I find the y-intercepts by plugging 0 in for x, but I can't. X can't be 0. So if I try to plug in 0 for x, I see, whoa, I get a 0 in the denominator. That's undefined, no y-intercept, just like we saw on example 4 in this series of examples. For x-intercepts, we set the y value to 0, the output to 0, setting the numerator equal to 0 as we've done in every example so far, and something interesting happens here as well. I get 0 equals 1. 0 can't equal 1. So we have another situation where we can't have an intercept there. We can't have a solution to that equation. It doesn't work. So no x-intercept. So a fine bit of work we've done so far, we have found nothing. Moving on. From intercepts to asymptotes. We can find asymptotes, set that denominator, as we've done before, set that denominator equal to 0, x minus 1 equals 0, and we get x equals 1. Note that we're not taking the x factor and setting it equal to 0 for a vertical asymptote. Because the x factors canceled and I was only left with an x minus 1 factor in the denominator, then it's just that x minus 1 factor that comes into play for my vertical asymptotes. The x that reduced does affect the graph, but not as a vertical asymptote. We'll take a look at that on the next slide. For now, it's enough to say we've got a vertical asymptote at x equals 1, and that is our only vertical asymptote. So we set the reduced denominator equal to 0 to find our vertical asymptote. For the horizontal asymptote, we recognize the degree of the numerator smaller than the degree of the denominator. So we once again have y equals 0 as our horizontal asymptote. Now let's talk about what happens with that factor of x that canceled in the numerator and denominator. That turns out to be what we call, in fancy math terms, a removable discontinuity. Another way of stating that in a little bit more plain English is it's going to be a hole in the graph of the function. A point that x can't be, the curve can't exist there, but it exists both to the left and to the right, and it's not a vertical asymptote. So it's what we call a removable discontinuity. It's a hole in the graph, and we'll see. I'll plot the graph, I'll sketch the graph, and we'll see what that looks like. To find where that hole occurs, we say, well, it's the x value 0 that's the culprit here. That x factor that canceled, that's an x value of 0. So we're going to take that x value of 0 and plug it into the function, the reduced function. When I plug that in, that x value of 0 into the reduced function, I get 1 over 0 minus 1, which is -1. So the point 0, -1 is not a point on the graph. It is where the hole in the graph ends up being. So I've got a hole in the graph at 0, -1, and I've got a couple of asymptotes that we can sketch. And I've done that here. There's the asymptote of y equals 0, horizontal asymptote, vertical asymptote at x equals 1, and a hole in the graph. So the graph exists around the point 0, -1, but not at the point 0, -1. From there, we could use a little bit more. Obviously, we haven't completed the graph, so we get at least one additional point here to the right of that vertical asymptote. X equals 2, plugging in 2 for the x value gives us, whether we plug it into the original function or the reduced function, doesn't matter, we get the same y value of -1 here. So the point 2 comma, did I say -1? The point 2 comma +1 is our additional point on the graph. So if we plot that point at 2 comma +1, and we don't have a point at 0, -1, but we've got some information that the graph exists around that point, just not at that point. There's a hole in the graph there. Then that actually gives us enough information to say from that hole in the graph, we are going to curve toward both the vertical and horizontal asymptotes. And from that new point, that additional point 2 comma 1, we're going to curve toward the horizontal and vertical asymptotes. And so we've got enough information now, just enough information to give a sketch of the curve of the graph of this function.